Today we're taking a look at section 2.3, which is Transformations and Symmetry. We've talked a little bit about symmetry in intermediate algebra. We have not talked about transformations yet. So I actually think transformations are a really fun section. So the idea of a transformation is you're taking one of those basic graphs we did in the last section, and we had 7 of them, I think, and we're moving them up and down and left and right, and we're stretching them out of shape. That's what transformational geometry is about. All right, so the first one we're going to talk about is a vertical translation. A vertical translation takes an equation, so we'll call our equation g of x. Okay? And then it either adds or subtracts, I'm just going to put plus right now, a number on the on the outside, like after the equation. So you just put a plus something at the end or a minus something at the end.
Does that just leave it like up and down?
Yes, it does. So if the h value is positive or if the h value is negative, okay, so h value positive means it looks like we're adding something to the end. If the h value is negative, it looks like we're subtracting something at the end. So everything happens the way you would expect it to happen when you add or subtract a number to a function. It's a vertical transformation. If you add it, do you think you'd move it up or down? Up. So this is a shift up. And if you were subtracting it, you would expect it to go down. So this is a shift down.
What'd you call me? I'm just kidding.
And let me give you an example of an actual equation where you could see that happening. So this will be our function f of x equals x squared and then minus 3. So we take that x squared graph and we would do what with it?
You would move it.
Move it down 3. Yeah, that's what that would mean. Okay? So it's a shift of the whole thing. It's just like taking it physically and moving it down 3, like you standing in an elevator and going down 3 floors. Right? You didn't lose weight. You didn't change your shape. You just changed location. That's all it does. All right, horizontal translation. So what do you think that does? Left and right. No reflections just yet. We'll get there. But it moves it left or right. So what that one actually looks like is it looks like your equation where you manipulate on the inside. We actually will put it as plus h inside of the parentheses instead of after the parentheses. Now anything that's done horizontally, left and right, is counterintuitive. Right? We add on the outside, it moves it up. We subtract on the outside, it moves it down. But when our value is actually positive on the inside, it does not shift it right, it actually shifts left. And if it's negative on the inside, it actually shifts right.
I was sitting out there and I was like,
That means it's positive on the inside?
Yes, if you shift it left, it's because it's positive on the inside.
if you shift right, that means
It would have been negative on the inside. Right. I mean, correct. So, an example. We'll do f of x equals x minus 3. So it's inside with the x, and then I'm going to put a squared on the outside of it. And how would it shift it, Haley?
shift right or shift
Yeah, it would be a shift right 3. So this one would move right 3. I said it, but I didn't write it. This one would have moved at the beginning that was down 3. Okay, so up and down, left and right. That's translations. There's a second kind of transformation that we're going to talk about, and it's called a reflection. So a reflection starts to look like some of the things we saw when we were talking about symmetry.
That's not till the next step.
Oh, I'm not there yet. I wanted to do examples. That's true. Okay, we'll push pause on my reflections argument. I'll tell you that in a minute. Okay, let's do an example. Sorry. I was just getting ahead of myself. I was so excited to tell you about the next type. All right, so these two then have those kinds of shifts that we just talked about. So in the first one, it has a plus 2. Is the plus 2 inside or outside? Outside. So will it shift it how? Up or down, and this one is up. So this piece right here says I'm going to move up 2. So I'm going to draw something that I don't necessarily want you to draw. It's your choice if you want to draw it. But I'm going to draw the original graph of absolute value x first on my graph, and then I'm going to do the shift. Okay, so if you don't want to draw it, don't draw it. But I just want you to see how it actually ends up looking if you sort of think about the visual imagery of what's happening. So our original graph of absolute value of x, it crosses at the origin, it crosses at 1, 1, it crosses at negative 1, 1, and it's a V shape. That's my absolute value graph. It looks like this. Okay. This is my original graph of y equals the absolute value of x. We did this last time. That's my basic graph. I don't know why it looks uneven, but I just didn't make them long enough.
From the last.
Yeah, from the last chapter. All right, we'll go with that. What this graph is going to do then is shift up 2. From where you were, you're going to move it up 2. So instead of hitting the origin, it's actually going to cross right here at a height of 2. I'll do it in black. So it'll cross right here. And then, like what we really did is sort of from that origin spot, we went up 1 and left and right 1. Can you kind of sense that, right? So this actually goes up 1 and right 1, up 1 and left 1. We can do that same imagery from my new shifted graph. I can go up 1 and right 1. That'll put me here. Up 1 and left 1 will put me here. And the new graph is actually like this. So they kind of look nested inside of each other because you just shifted it up or down. And this one we went up. So when you draw these, you don't necessarily need to draw the original graph. I just wanted you to see that for the first time we did it, so you can see how it looks on a graph.
So on
As
our
it's shifted.
test, like when it asks us that equation, do you want us to draw like the second one you did?
Yes, the black one I did that's in black. Yeah. Okay. So how about this other one, this other equation on number 2? Is it shifted left or right, up or down? Okay, it's horizontal because it's inside. And by inside, we mean inside the absolute values, right? This is a horizontal shift. Is it right or left?
Right.
It's right. So this will move us right 2. Okay, so I'm not going to draw the graph every time. I'm not going to draw it again on this one. But we're just going to take that original graph of absolute value x, and I'm going to move it right 2. Okay? So right 2 would mean that it would be moving from over here. So my x-intercept here now looks like that point at 2 because I moved right 2. And then I would go up 1 and right, up 1 and left from that location. And then I'll connect my dots.
So whenever you graphically add 2,
Yep.
like is this, for not all the problems, but the problems like this, you just go up 1, over 1.
For many of them, we will. Yeah, so absolute value of x looks like that. X squared looks like that. X cubed, you go up 1 and right 1, down 1 and left 1. But ones and ones are often very nice and friendly, and they show up in a lot of places. Okay. Any questions on transformations with the translations? Left, right, up, down. Okay. Reflections then. That's where I was trying to get to. Reflections. So reflections take graphs and they either reflect it over the y-axis like this or over the x-axis like this. Those are our 2 kinds of reflections. So we have a vertical reflection that goes up and down, right? It flips it from top to bottom or from bottom to top. And then we have a horizontal reflection that flips it from left to right or right to left. Now, some of our graphs are very nice and pretty already. So like if you take a look at the equation over here that's in white on the very first graph, if I reflected that over the x and the y, over the y-axis, it wouldn't look any different. Because the stuff that's on the left would land on the right, and the stuff that's on the right would land on the left. It wouldn't actually affect any change. So that happens sometimes. But a lot of times, of course, it does not. So the 2 kinds of reflections have negatives occur in different locations. So one option is that there is a negative that occurs on the inside with x. The other option is that there's a negative that occurs in front of the whole equation. So you can kind of imagine in terms of that absolute values that I saw, you'd have the absolute values inside, the negative inside the absolute values. On the other one, you'd have the negative in front of the absolute value. That's what that would look like visually. So if you have the negative happening inside, anything that happens inside is a horizontal change, right? Over here, it happened inside, it affected it horizontally, shifting it left and right. If it happens outside, it affected it vertically, shifting it up and down. So again, the negative on the inside is a horizontal reflection. So what does that mean? Well, it means it's a reflection over the y-axis. I promise I'll draw pictures in a minute, but just write the details down for the moment, okay? If it's happening on the outside, right, on the negative is at the beginning of the equation, this is a vertical reflection. And this is a reflection over, over the x-axis. So with my absolute value graph, if I put a negative on the inside, it wouldn't change the graph at all, because reflecting over the y-axis wouldn't change the image, right? It would be like you making handprints and then figuring out how you would look if you flipped your handprints. Well, it'd look exactly the same, right, if you flipped it between where your thumbs hit. But if you reflected the absolute value graph over the x-axis, it would actually flip it upside down, and it would look different. The last type of transformation we're going to talk about is a vertical stretch or shrink. Now, I am purposely not talking about one of the types of reflections, not reflections, but stretches. I'm not talking about a horizontal one. And the reason I'm not is because you can always think of it as a vertical one, and it takes care of both images. So let me explain. A vertical stretch or shrink looks like a number in front of our function. Okay, I'm going to call it k. If k is positive, I don't think I wrote that right. If k is greater than 1, that's what I actually wanted to write. K is greater than 1. This is a stretch. And I want to remind you, it's a stretch vertically. i.e., things end up looking skinnier. That is not a math term. And if your k value is between 0 and 1, it's a shrink. Again, vertically. And I'm going to hesitate by saying fatter because I don't really think that's what it looks like when you do it. I think it makes it look flatter. And again, I'll draw images so you can see what I mean. But those are the words that sort of ring true when you see these images happen. They look skinnier or they look flatter. So what I want you to imagine is I want you to imagine the Play-Doh thing that comes out when you first get a thing of Play-Doh. Has everybody played with Play-Doh before? Okay, if you haven't, imagine clay. Somebody played with something, right? You've got the Play-Doh and it's in this like cylinder shape. If it's a vertical stretch, it's like you're pulling it like this, right? You're stretching it out like this, and it looks skinnier when you do that, right? It takes it from looking like a toilet paper roll to looking like a paper towel roll, tall and skinny, all right? If you're doing a horizontal or a vertical shrink, you're squishing it flatter, all right? So you're making it squish down. So it ends up making something look more like a donut shape if you squished it, right? Filled in donut, but it looked like a donut shape when you squished it, and so it would look flatter. All right, so those are the two different types of vertical stretch shrink, and then I had reflections. I forgot to write my examples on these, so let me go back and actually give you an example of each of them so you can actually see them. I need to make this smaller to do that. So if you have a reflection and it was on the outside, it might look, on the inside, it might look like this, right? It's inside. It's actually inside the absolute, or in this case, not absolute value, but the radical. And if you did it on the outside, it would look like this. It's outside the radical. Okay, so the first one would reflect it over the y-axis. The second one would reflect it over the x-axis, up and down. If you were dealing with a vertical stretch or shrink, you would have something that looked like this. So let's say we had f of x equals, and you have a number bigger than 1 is the goal. So I'll use 2. You have 2x squared. Or I actually used cubed in my notes. I'll use cubed so it matches. 2x cubed. All right? But then the other option then instead is that you have 1/2 x cubed. Right? It's a number that's between 0 and 1. It's going to be a fraction. We tend to see fractions and not decimals, but it's a fraction between 0 and 1. All right, some examples now. All right, so the first one is one I've been talking about doing. We just haven't done it yet. It's got a negative. Is it inside or outside? Outside. So if it's outside, will it reflect it left, right, or up, down? Vertical, so up, down. Okay? So the original graph of absolute value of x, I'm just going to sketch it in, look like that. That's terrible. How about that, more or less? So if I take this image, I'll draw it better on my actual reflection, and I reflect it up or down, will it reflect, what will it reflect to look like? It'll reflect over the x-axis, it'll flip and look like an upside down V, right? So my image will be the 0, 0, and then instead of going right and left and up 1, I'll go right and left and down 1. So it'll end up looking like this. Okay, so I'm flipping things down. What's number 4 going to do? It's going to shrink. So this is a vertical shrink, which makes it look flatter. Again, let me draw both images for you so you can see what happens. So the original image looks something like this if I draw it, just as a sketch, of course. And what we're going to do is we're going to, it's called a compression as well. We're going to compress it down. We're going to push down from the top, and so it's going to stretch it out to the sides, right? But when we're thinking vertically, it's a compression or a shrink. So what happens is that instead of going right and left 1 and up, up 1, what we do is we go right 3 and up 1. It acts kind of like slope. So instead of going up 1 and right and left 1, we go up 1 and right and left 3. And my image ends up looking like this. Whereas originally, I'll draw it in the black, it looked something more like this. Right? So you take it and you just squish it down like the Play-Doh. It flattens it.
Green is like the shrink flatter one.
Yeah. Okay, so I've squished it down. And if you're not sure, like, well, how do I decide if I go up and right, left and right, 1 and negative? What do I do? How did I make that decision? Well, if you actually take a look, the reason that I'm able to say that is because I've chosen some values that are very nice. Obviously, if I put 0 into this equation, I get out 0. Because when I multiply 0 by things, they stay 0, right? So this is h of x. But if I put in, say, x equal 3, the absolute value of 3 is 3, and then what's 1/3 times 3? 1. So I went 3, 1, and I could do the same thing with negative 3, 1. Because the absolute value of negative 3 would also be 3, times the 1/3 would be 1. Okay, so there's a visual appeal to it that sort of says, oh, I do this in this way, but you can also do concrete number crunching if you want to. If you didn't want to use 3 and 1, you could actually choose to use like the number 1 we did before, and it'd be 1 and 1/3, and that'd be okay. So you'd go over to the right 1, and you'd only go up 1/3. You could do it from that perspective too, to get sort of some sort of perspective of how squished it is from your graph. All right, not only are we going to take equations and graph them, you're also going to be given verbal descriptions and asked to write an equation. So here's an example of that. You're going to write an equation of the graph that does this. It's the graph of y equal x squared. But it wants you to move it right 4 and down 7. So how will I get it to move right 4? First of all, do we need to add or subtract? It will be a subtraction of 4. And where will it occur? Inside or outside? Inside. So I'm just going to jot down some details for us. Down 7, will I add or subtract 7? Subtract 7. Will I do it on the inside or the outside? On the outside. So what does it mean by inside and outside? Well, it means inside and outside of the squaring. The squaring is what's happening to the values, right? So when I think about writing this out, what is my equation's name? Y. So we will write y equals, just because it's already been given to us as y. There will be something squared, and I need to do something inside of the squaring. It's the -4 part.
X minus 5.
And then the -7 needs to occur on the outside of the squaring. And it would look like that. The -4 moves it right 4. The -7 moves it down 7. Now, a lot of you have calculators that graph. All of you have computers that graph. Just pull up a graphing computer, right? Disk. So if you wanted to confirm that you were thinking of it in the right way, and you didn't just want to, do it inside of My Math Web, which of course will tell you if you've made a mistake, but if you wanted to confirm it before you just put it in, you could graph this, right?
Yeah.
And if you looked at the graph of x minus 4 squared and -7, it should look like the description that you were given. It should look like a parabola, an x squared graph, that's been moved right 4 and down 7. So visually, you should be able to be like, yep, I moved it in the right way. Whereas let's say you messed up a sign and you put this as +4 here. If you graph that, you're going to be like, whoa, 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 that went the wrong direction. What did I do? And you should realize, oh, look, I put a plus instead of a minus. Oh, that's right. Inside things happen backwards. Something like that. Let me undo it because we want it to be right. All right, B. We've got the graph of square root of x. It's stretched vertically by a factor of 4. That's one feature. So what does it mean when I'm going to be stretching it vertically by a factor of 4? The k value is going to be 4. So I'm going to actually have a 4 and it's going to be multiplied, right? So when I shift things left and right, up and down, I add and subtract values. But when I do reflections, I multiply by negatives. When I do vertical stretching or shrinking, I multiply by numbers. So in this case, it's a 4. Reflected over the x-axis. So there's a negative. Will it be on the negative on the outside or on the inside?
Outside.
Yeah, there will be a negative on the outside. And again, if you get it wrong and you just look at your graph real quick, you should be able to confirm that you did it wrong and see that it didn't do what you expected it to do and then adjust. How do I get it to go up 3? Add 3 where? On the outside. Okay, so let's put it all together. We have y equals. You've told me to put a -4 or negative on the outside. My 4 is always on the outside, the way it's been described. I have a square root graph of x like that. And then again, something else happening on the outside, it's the +3. Make sure your +3 is not showing up accidentally underneath the radical. That would be inside. Okay, and it said +3 because it's up 3. Okay, there's a lot going on in that one.
Yeah.
Now, we're going to take some and we're take a look at how to think about how we graph them when we're given lots of details. Like over here, I only had one change made, right? One at a time. Over here, there's only one change made. What happens if I were actually having to graph the equation that I just made on this part B? There's 3 changes there. How do I decide what change I operate with first? Do I move up first? Do I reflect first? Do I multiply by 4 first? Which is my first operation? Well, there is an ordering to it, kind of like order of operations. This is order of transformations. The order of transformations always occurs from the inside out. Okay? It's kind of like when we're solving equations. We work from the, or for simplifying expressions is what I meant to say. We work from the inside out. So inside will be the things that happen in here. which is always the horizontal shifts, moving it left or right. So the first thing that we do is we do anything we need to do that shifts left or right. The second one, the reflect and also we would, this is not written in here well. This would also include any reflections inside. Yes. I don't know why it's written that way, but I think it's just identifying it from here is what it's showing you, that it's the negative h in the equation above. That's what it's doing. This also includes the reflections over the y-axis. We would do those first as well because they occur inside. We're doing the things inside first is the point. So shifting things left and right, any reflections over the y-axis. I don't have it in this particular, how this is set up here. There's not a reflection. The second thing, number 2, is reflect and vertical stretches or shrinks. So any reflections that go over, so this is reflections over the y-axis, that's what that means, and vertical stretches or shrinks. So we're going to stretch it up, we're going to shrink it down, okay, compress. And the last thing to do is the vertical translation, which means to take the whole graph and shift it up or down. That's our very last step.
Is that supposed to be over x-axis on 2?
Oh, I wrote it twice, didn't I? Yes, it is. Thank you. Got one wrong. There we go. Reflective over x-axis. This is the second one. Thank you, Maxwell. Okay, now look. If you look back at the actual expression, that sort of makes sense. The first thing we're doing is we're working on the inside. So whatever's happening inside, we do that first. And the next thing that's most attached is we work with multiplication, right? So we could be multiplying by negative, we can multiply by positive, we can multiply by a number that's 1 or by something bigger than 1. And then the final last thing is the addition or subtraction on the very end. It's always inside out. So work from the inside out. All right, so you know what? Let's actually graph that last one. I don't have an example of one of those to be graphed, and I think that would be helpful to see. So let's actually do this equation right here. That's y equals 4 square root x plus 3. I'll show you a cool feature I have on my screen. I'll make it big. How about that one? Is that easier to see? Okay, so we're working with an equation that says right now y equals negative 4 square root of x plus 3. That's the equation that I was working with on that last problem. So notice there aren't any transformations inside, right? It's just x inside. So I'm not shifting it left or right. I'm not reflecting it over the y-axis. There's no horizontal changes going on. The only changes that I have going on, or the first changes that I have going on, are this, whoops, I meant to highlight, this 4 right here and this negative right here. So let's say that we were starting from scratch. I know we had descriptions that we created this from. But that 4 tells you that you're stretching it up 4, right? And the negative tells you you're reflecting it down. So my original graph of square root of x looked like this. It goes through 0, 0, and 1, 1, and it looked like that half of a parabola. That's what it looked like. So the multiplying by 4 tells me that instead of going through 1, 1, it's going to go through 1, 4. So imagery, if I just had the multiplication by 4, I'd now have this really tall graph. But there's a negative, which means this really tall graph now needs to flip underneath the axis. So now instead, I'm down here. I don't have enough space now down here, so I need to move this. Give me a sec. Okay, so instead of being up at 4, we're going to be down at negative 4. All right? And so there's this kind of a graph is what I have right now going on. That's terrible. Absolutely horribly ugly. I know. And then what's that plus 3 at the end going to do? It's going to move everything up 3. So let me change colors so that I can do that. So the origin is now going to be here. That is a terrible pen.
Is that up? I'm sorry.
there we go. So from my origin, I went up 3. From this point that's -4 down here, I'm going up 3, so now I'm right there. And if I connect these, they'll look something like that. Okay, so the first thing I did is I stretched it up to go through the number 4. The second thing I did is I reflected it down underneath the axis to -4, and then I took those 2 points and I just physically moved them up 3 times.
It's so curvy.
It's very curvy. And I've got an enlarged screen, so that's also making it look that way too. Okay, I'd like to go back then and we'll finish the parts that we were going to talk about, the special symmetries. We've talked about some of these before already in intermediate, so some of this will look like review. Okay, there are 2 special symmetries that happen with functions. Specifically, we're working with functions. The first is called y-axis symmetry. And when that happens, the function is called even. And an example that you have had of an even function just today already is the absolute value of x. It has symmetry over the y-axis. Another one that we have seen very recently is the parabola. Parabola has beautiful symmetry over the y-axis. The y-axis sort of looks like it's cutting the graph in half. Perfectly even halves. So it feels even. That's what you're talking about, right, Abby? Yeah, so I thought. Okay. Origin symmetry is my other one. So my origin symmetry is called an odd function. And it's not odd in the sense of weird. It's even and odd, so that's where they're getting the other word, right? There's a comparison there too. Graphs are odd if they have origin symmetry, so that's fabulous because that's alliteration, right? OO. I think that's great. Anytime there's those fun things that show up, it's helpful. You've seen in examples of this too. An example that you have seen of this is y equals x cubed. It's odd. And so let me remind you of that graph because that's probably less familiar to you than the other 2 I just drew or just explained. If I were to rotate this 180 degrees around the origin, it would land back on itself. That's what origin symmetry means. Origin symmetry means it's like a spinner in a game. If I spin it 180 degrees, I have the same graph. So this was an example of one. Another example that we had in the last section is we actually had the cube root of x. Probably not a familiar graph if I just leave you with it hanging like that. So let me draw it too. This is actually what it looks like. It looks like my cube graph sort of on its side in some way. Again, if I spin that 180 degrees, it would land down right on itself. Okay, so those are odd graphs.
So do we just, like, if we're looking at an equation like we're about to do we just look at the numbers and if they're even, then it's even, and if it's odd, it's odd?
Yeah, so let me show you how we're going to deal with it because it's a little bit more than just that because we're not going to only be looking at the graphs that we've done, right? Those basic 7. It's not just those graphs. So when we dealt with this at the very end to intermediate, you were sometimes given graphs that looked kind of wonky, right? It was the very last question on your last exam for me for that class. Is that you were given 3 graphs and you were told, decide, does it have even, is it have x-axis symmetry, y-axis symmetry, origin symmetry, or none of the above? And you were supposed to mark all that applied. Remember that question? Mm-hmm. Okay, so you were doing it in intermediate from the perspective of looking at a graph. And so you were doing it sort of visually. We're going to do it now from an algebraic standpoint. So let me show you what it means to do this from an algebraic standpoint. From an algebraic standpoint, a function is even if you multiply by a negative inside with x, and it doesn't change anything. It looks exactly the same. But that should make sense. If I took a graph of x squared and I rotated it or I flipped it over the y-axis, nothing would change. In a very real sense, what would be happening is that this point right here and this point right here, if I rotated it over the y-axis, would just swap. So visually, they don't look any different, right? So this is, let me draw it. Sorry, that's really thick. If this was my graph of y equal x squared and I rotated it, right, like this, just rotated it around the y-axis, everything would land back on itself. So what used to be right here on the positive side would now be on the negative side, but visually speaking, none of the graph overall changes. Now, origin, symmetry, odd functions are a little bit trickier. Instead of looking the same when I multiply on the inside by a negative, they actually look exactly opposite. So everything that was positive is now negative, and everything that was negative is now positive. So again, from the graphs that I've drawn, here's what you can see. This point right here, right 1, right? And it was positive 1, is now left 1. It's the same value, but now it's negative 1. All my values switched. Okay? That's how it relates back to the imagery that we were doing before. So let me show you 3 examples. Obviously, I've chosen 3 examples because I want you to see one that works out odd, one that works out even, and one that works out to being neither. Okay? Can you confirm with your calculator? Absolutely. In fact, I would encourage you to do so. But I'm going to expect to see that you can show me algebraically why it works as well, without question. So let me show you how it works. No matter which one you're looking for, you're always testing what is f of negative x. What happens when I take my x's and I replace them all with a negative x? So this is the checking ability that we have every time we do the exact same thing. We put in negative x for all the x's. Now, what happens when I multiply a negative by itself 4 times?
It's positive.
It's positive, right? So I can put the negative x inside of here, and then I can raise it to the power 4th, but it doesn't change anything because a negative times itself 4 times is a positive. So this is still just x to the 4th because it happened 4 times. What about this negative in here twice? Also a positive. So the negative 2 at the front stays the same right there, and this negative x squared is just x squared. So compare x to the 4th minus 2x squared to the original x to the 4th minus 2x squared, and what do you see?
It's the same.
It's exactly the same. Nothing changed.
It's even.
So this one right here is exactly the same as what I started with, and that's my definition, like you just said, for even. Okay, let's move over to part B. So on part B, actually let me do C first. I like C better. I think it'll make more sense to you in this order. I probably should have done it differently. That's okay. All right, so we're going to put negative in for all my x's. We're going to do C first. So we're going to replace the x here with negative x. We're going to replace the x here with negative x. And we're going to go from there. Okay, everybody good so far? Just a replacement. The first step you should always be able to do. All it is a replacement step. Now, what happens when you multiply a negative by itself 3 times? It stays negative. You guys are already getting ahead of yourselves with the odds, so hold that tight to that ideology for the moment. It just stays negative. But it's still cubed, but it's just negative, right? The negative stays. When I did it 4 times, the negative disappeared. When I do it 3 times, the negative sticks around. Now, I want you to think about a specific number. I'm going to use a number that you're familiar with. We're going to use the number 27. What's the cube root of 27?
9.
That's the square root of, no, it's not 9. I'm just trying to help you out. You said 9. It's 3. It's 3.
Oh my god.
Yeah, hold tight. Okay, it is 3. Okay, the cube root of 27 is 3. What happens if I do the cube root of negative 27? It's negative 3, right? And it's negative 3 because negative 3 times negative 3 times negative 3 is negative. So what happens when we do the cube root of a negative is that the negative stays, 2, right? It does. The negative actually is still there. So we actually end up with down here a negative cube root of x. Kind of looks like the negative came out. I get that. But really, it just means I end up with a negative value for whatever the cube root was. right? This is the exact same thing that would have happened if I said, okay, well, let's just put a negative in front of the 27. And I would have gotten a -3 just the same way.
So we don't do the I thing?
It's not square roots. This is a cube root. Yeah, imaginary numbers come about with square roots, not cube roots. Okay, whoops. So taking a look at this then, how does that compare to the original f of x function?
It's the opposite.
Exactly the opposite. All my signs switched, right? All of them. So it's exactly the opposite of what I began with. And the opposite of what I began with is exactly the definition of an odd function. Odd, opposite of what I began with. Origin, symmetry. It's odd. Now the last one, obviously the answer must be that it's neither, because that's why I'm doing it, is I want you to see what happens and how you discern that it's different. So what I actually want to do, because I think it'll be the easiest for you to see, is I want to multiply this out. X minus 1 times x minus 1, and sparing you the details for the moment, this will give you x squared minus 2x plus 1. Okay? I know we would FOIL it and all that good stuff, but we combine. All I've done so far is just multiply the function out. Okay? I'm going to go from here then to test that it's even or odd. So I'm going to do f of negative x here now. So I'm going to replace my x with negative x. So negative x squared minus 2 times negative x and plus 1. I'm pretty good so far. Okay.
You, like, distributed, both the x, well, never mind.
Okay.
Got it.
There are more ways to do the problem, so you might be thinking of another option.
Yeah.
But this, I think, maybe is the simplest to see that it's not going to get you either of them.
Yeah.
Okay, so what is negative x if you square it? It's positive, so it gives you just x squared. What happens when I have the negative 2 times the negative x? It's positive x. And it's a 2 still, so it's positive 2x. And then I have my plus 1 at the end. Okay, pretty good so far with the simplification. Okay, my negatives all did what they did. Now, if you compare this to this, tell me some of the things that you notice. There is a sign that changed, but they didn't all change, right? Just one of them. So some of them stayed the same, and some of them changed. Well, that's neither. Because in order to be even, they have to all stay the same. And in order to be odd, they have to all change. This did some of both. So this one would be neither. And that's my justification for it. So here's the cool thing about test questions or quiz questions. So hold on tight. Don't move just a second. Just listen real carefully. Let's say, for instance, you did the problem and you did it appropriately with all the negatives going through, whatever, and you made an error. Because we all make mistakes, right? Yeah, it happens. But whatever you answer for me in terms of it's even or it's odd or it's neither is based on your work. Now, my math lab doesn't work like that, right? Because it's got sort of constraints because it's technology and it's not me, right? I don't have constraints. I can look at your work and I can say, oh, look, they just made this one tiny little sign error, but then they interpreted their results properly when they were done, right? See, you couldn't do that in intermediate when all I was asking you to do was just look at a graph and I had to be like, well, I don't know what they really thought they were seeing. Maybe they thought about it right and they made this one small error and maybe they didn't. So it was more like all or nothing. Here you have better flexibility because it's not all or nothing anymore. Okay? All right, I will see you guys tomorrow. Have a great evening.